This is the third part of lecture 21. We continue with examples of Laplace transform. So I'm going to do example 6 now. Suppose, so if the Laplace transform of a function f is capital F of s for real part of s greater than, let's say, some number b, what is the Laplace transform of e to the at times the function f? So what effect does multiplying with the exponential function have on the Laplace transform of a function? Okay, so I'm going to use the definition. By definition, the Laplace transform is the improper integral from 0 to infinity e to the minus st times the function, which is e to the power at times f of t dt. So this is going to be, if I combine the exponential functions, keep the minus sign, minus s minus a times t, f of t dt. Now, remember we have the Laplace transform of the function f. By definition, it is e to the minus the integral from 0 to infinity of e to the minus st f of t dt. So if you compare these two, you see that the difference is in one of the integrals we have s and the other one we have s minus a. So instead of s, if I put s minus a, it means on the other side, instead of s, I use s minus a. So that means the Laplace transform of e to the at times the function is capital F of s minus a. Now, okay, now, so the origin, so this one, the Laplace transform of the function f is valid when real part of s is greater than b. Now, I replaced s with s minus a, so in this formula, I should have real part of s minus a greater than b. But real part of s minus a is real part of s minus real part of a. So this formula is valid for real part of s greater than real part of a plus b. Okay, so we take the number b, which comes from the original Laplace transform of the function f, and to b, we add the real part of the coefficient of t in the exponential function to obtain what? To obtain the interval for s. Okay, I'm going to do more examples on how to use this, but before considering more general examples, let's, or maybe here, let me say example 6a. What is going to be the Laplace transform of the function e to the minus 2t times sine of square root of 3t? So I want to use the above example. So the number a here is minus 2, real number, my function f of t is sine square root of 3t. By a previous example, we know that the Laplace transform of sine square root of 3t is, okay, coefficient of t is root 3. So this is root 3 over s squared plus root 3 squared. So root 3 squared is 3, and this is for s greater than 0, remember. So the number b here is 0. So when I multiply the sine function with e to the minus 2t, on the other side, I replace s with s minus minus 2. And now s becomes greater than a real part of a. A is minus 2, so s greater than minus 2 plus 0. Okay. So if I rewrite this, so Laplace transform of e to the minus 2t sine root 3t is root 3 over s plus 2 squared plus 3. And this is for s greater than minus 2. Okay? So this is how you use the formula. You get the Laplace transform of the function, and in the function, you replace s with s minus a, where a comes from the exponential part. Okay. Now, example 7. So this is going to be the generalization of the Laplace transform of the polynomial t to the n. So again, we have a Laplace transform of some function f given, say f of s, for real part of s greater than b. By the way, in the above example, I should have taken real part of s greater than minus 2 for complex s. Okay. Okay. So if this is the case, then what is the Laplace transform of t times f of t? Okay, again, I'm going to use the definition. By definition, this is the integral, let me see, this is the integral from 0 to infinity e to the minus st t f of t dt. So somehow, in order to use the Laplace transform of f, somehow I have to get rid of this p. I have to get rid of this t, or I need to figure out a way. Okay, what is the definition of the Laplace transform of the function f? 0 to infinity e to the minus st f of t dt. So I need to find a transformation which transforms one of these integral into the other. And here it turns out to be taking the derivative of this integral with respect to s. So I take the derivative of this function with respect to s. I take the derivative of this integral Now, for the next step, how I'm going to take the derivative of this integral. The integral is with respect to t, but the derivative is with respect to s. So somehow, since s and t are independent, this should be the integral of the derivative with respect to s. We should be able to interchange the integral and the derivative. And of course, we cannot do this arbitrarily. The function should satisfy certain properties, but these are nice functions, integrable, where this improper integral is convergent. This is a result. This is by a result from advanced calculus, so not suitable to do here. So the integral is with respect to t, but the derivative is with respect to s, so we can interchange the order of integration and the derivative. Okay, so what is the derivative? E to the minus st with respect to s. So the derivative is minus t, e to the minus st. And of course, f of t doesn't depend on s, so it's like a constant. So we have minus the integral e to the minus st, t, f of t, dt. So I have minus the Laplace transform of t, f of t. So Laplace transform of t, f of t is minus the derivative with respect to s of Laplace transform of f of t. So multiplication by t means, in the t world, means in the transform world, in the s world, it means taking the derivative. In the t world, we multiply by t. In the s world, we take the derivative with respect to t. Okay, so we can apply this to, so example 7a, we can apply this to an example we already did, Laplace transform of t to the n is greater than or equal to 1. So I consider this t times t to the n minus 1. Okay, so this is minus Laplace transform of t to the n minus 1. Minus the derivative with respect to s. Okay, and if you keep going like this, so this is minus derivative with respect to s of Laplace transform of t to the n minus 2. So second derivative with respect to s of t to the n minus 2. So minus the third derivative with respect to s of t to the n minus 3. So if you keep going like this, we get, okay, to get constant 1, I need to take the antiderivative. So minus 1 to the n, derivative with antiderivative with respect to s, and inside I get the constant function 1. So I have minus 1 to the n, the antiderivative of the function 1 over s, but this is minus 1 to the n factorial over s to the n plus 1. So we have n factorial s to the n plus 1. And since the original one, Laplace transform of 1, is equal to s for s greater than, a real part of s greater than 0, this final formula also works for real part of s greater than 0. So we get the same result now using this formula. Multiplication by t means taking the derivative with respect to s of the Laplace transform of the function. So maybe another example. Now, example 8. Again, this idea of Laplace transform of multiplication by t. What is the Laplace transform of t squared cosine 2t? Now, we know that Laplace transform of cosine 2t is s over s squared plus 4. Coefficient of t is 2, so the number a is 2. 2 squared is 4. S over s squared plus 4 for real part of s greater than 0. So if you multiply with t, we have minus derivative with respect to s of this function, which is minus derivative of s is 1 times denominator, minus s times derivative of the denominator is 2s over s squared plus 4 squared. So minus s squared minus s squared plus 4, s squared plus 4 squared, or s squared minus 4 over s squared plus 4 squared. And now if you multiply with another t, we have minus derivative with respect to s of this function. Okay, so derivative of the numerator 2s times denominator minus the numerator derivative of the denominator over denominator squared. And if you simplify s squared plus 4s and factor out the 2s in the numerator, here I have, in the first part, I have s squared plus 4. If I factor out 2s, s squared plus 4 is canceled out, minus 2 times s squared minus 4. So minus 2s squared plus 8 over s squared plus 4 cubed. So this is minus 2s times minus s squared plus 12. So 2s times s squared minus 12 divided by s squared plus 4 cubed. This is the Laplace transform of t squared cosine 2t. This is again for real part of s greater than 0, because the original formula we use, Laplace transform of cosine function, is valid for real part of s greater than 0. So this one also for real part of s greater than 0. Okay. Now I want to do one last example to finish off this lecture. What is the Laplace transform of, so again, if the Laplace transform of the function f is capital F for real part of s greater than some number b, what is the Laplace transform of f of ct? Again, here c is a real number. Do we take a positive number? Okay, we will see. It will definitely, it is definitely not 0. Do we have to take it positive? Yes, I think so. So c greater than 0 constant. Okay, so what is the effect of changing the variable t by multiplication with a positive number c? Okay, so again, we are going to use the definition. The Laplace transform is the integral from 0 to infinity e to the minus st f of ct dt. So what we are going to do, basically, change the variable in the integration. We want to get rid of this c. So we let u to be c times t. Then du is c times dt. So dt is 1 over c times du. So the integral then becomes, when t is 0, u is also 0. And when t goes to infinity, oh, okay, that's why we take c positive. Since c is positive, as t goes to infinity, since c is positive, as t goes to infinity, u also goes to infinity. So again, the integral is from 0 to infinity. E to the minus s, but instead of t, now I write u over c. And instead of ct, I write u. And instead of dt, we write 1 over c du. So what we have is 1 over c, the integral from 0 to infinity, e to the minus s over c times u, f of u, du. Now remember that the function f have the Laplace transform capital F. The definition of capital F, e to the integral from 0 to infinity, e to the minus st, f of t, dt. So here, the variable of the integral is not important because we evaluate the integral, we take the improper integral. So instead of t, I can write u. So if I go back to my integral, Laplace transform of f of ct, first of all, I have 1 over c, and in integral, instead of s, I have s over c. So in capital F, instead of s, I use s over c. Okay, so Laplace transform of f of ct is 1 over c, capital F of s over c, and for which s, the condition for s is the same as the condition for s in the Laplace transform of f. So again, if the original formula is for real part of s greater than b, then this formula also works for real part of s greater than b. Okay, so these are just some examples. Of course, we can look at more examples, but I guess we should start by using this transform on solving differential equations. And in order to do that, first we need to figure out how the Laplace transform is affected if we take the derivative of the function f. So if the Laplace transform of f, so next what we are going to do, if the Laplace transform of the function f is capital F of s, and if f of t is differentiable, what is the Laplace transform of the derivative of f? So, and use this to transform differential equations. So this is going to be the content of the next lecture, but this is all for lecture 21. Okay, talk to you later.